So I'm going back to this earlier example from 2 videos ago when we were looking at just whether different things are functions or not. And I want to work with this but using the mapping notation now. So here we're assuming these are distinct, and that allowed us to know for sure that this is a function. Not proving, but just by inspection and making good guesses. So we think this is a function. We would probably think there was a problem if, if I put u here and if v didn't equal k, then this might not be a function. So if I had a u here, say, then I would want to make sure that v is here for this to still be a function. So here this is a function. And now can I write something using the mapping notation that is true? So something like f maps blah to blah. Can I write an assertion like this and have it be true? Well, remember that whenever you see a mapping assertion like this, it's actually asserting 3 things. That f is a function, that whatever is written here is the domain of f, and that whatever is written here contains the range of f as a subset. So in order to make this true, what I write down here to be true, I need to ensure that 3 things are true. That f is a function, and we've already thought about that, so that's good. So there's only 2 things left to ensure. That what I write here is the domain of f, so I will write down the domain of f, and that what I write here contains as a subset the range of f. So here I have only one choice as to what to write down. It has to be the domain of f. I mean, there are different ways of writing it, like x, w, u would also work, but it just has to be the domain of f. So I just selected the first positions. So far, so good. And then here I have to write down something which contains as a subset the range of f. So let's see. It at least needs to contain y, v, and k. Now it contains as a subset the range of f. But it's allowed to contain more things, so I could just throw in the number 3 here, just for fun, maybe the variable p, whatever that means, and this would still be true. So this is a true mapping statement. F maps the set consisting of x, u, and w to the set consisting of y, v, k, 3, and p. So this is true. Now what if I changed things so that f is not a function? So let's say here I put u. Then is this true? So now f is not a function. Then is this true? No, it's false, because this would assert 3 things, and one of those 3 things is that f is a function. But there's also a second reason that it's false, which is this also asserts that this is the domain, but it's no longer the domain. This is the domain, right? And w is not x or u, since I have assumed that everything's distinct here. So there's 2 reasons why this fails after I make the change. Let's see. So here I was allowed to list more things than are really in the range of f, and the mapping statement still ends up being true, right? What if I make this list without the k there? Then is this true? No, it's false, because again, this is asserting 3 things, and one of those 3 things is that the range of f is a subset of what's written here. And that's just false, because k is in there and k is not in there, right? Well, actually, I guess I don't know for sure that it's false, because I never told you that k is not equal to 3 or k is not equal to p. There. Now it's false for sure if I do this. So let's do another one. What about a function that is a singleton? You can have a function be a singleton. So like a comma b or something. Let's make it 1 comma 3. We haven't defined what 1 and 3 are, but you'll see later on they're going to end up just being some constants. So they are terms, so this is at least grammatically correct. Then what would you say about this? Is it a function? Well, 2 things. Is it a set of pairs? And does it have the big XYZ condition way back at the beginning here? It's definitely a set of pairs. Every element of this, all one of its elements, are indeed pairs, the pair 1, 3. And it indeed has that condition, that it satisfies that condition, that whenever you have two pairs in there, blah, blah, blah. Actually, anytime you have two pairs in there, they're actually going to be the same pair, 1, 3 and 1, 3. So the first positions will match and the second positions will match. So it's very easy to prove that this is a function. And so that means, since it is a function, that means we can at least write some kind of mapping notation like this. And what would go here and what would go here? So what do you think? See if you can fill in some symbols here and get this right. Okay, so I'm assuming maybe you paused the video and tried it, or whatever. You don't have to. Here's my answer. So here I have to put the domain. So if you put this here, you are correct. If you put pretty much anything else, you're probably wrong. If you put 1, then that would be wrong. It's singleton 1. That's the domain of this, right? What about over here? So this would be correct, to just put singleton 3. Also, I could list some other things like 2 and p. That would still be correct, because all I need to write here to make this assertion true is a set that contains the range as a subset. And the range is this. The range of this thing is this. Okay. How about another one? The empty set. So can I write something like this with the empty set? Yeah, the empty set is a function. So if I just stick its domain here, that's going to be the empty set. And if I stick any set containing the range here, so I can literally put any set here actually, since, you know, any given set is going to have the empty set as a subset. Right? This is their 13.1. The empty set is a subset of any given set. So I can actually literally write anything here, any term, and this will be true. We could write the empty set, and that's like the sort of smallest thing I can put here to make it true. But I could, if I feel like it, put singleton of the empty set or something else. I could put anything here, and this will be true. So the empty function takes as its inputs elements of the empty set. In other words, it takes no inputs. You can never plug anything into the empty function, but it is a function according to our definitions. So one last reminder before I end the lecture about the mapping notation. If you actually have the statement f maps x to y, then you can unpack that statement and you get three things out of that. So you get, looking at the definition of mapping, you get f is a function, domain f is x, range f is a subset of y. So when you have this, don't just be stuck and be like, I don't know what to do. You can unpack it into the three things that it means. And those three things, like a lot of them will unpack into further things. So that's where to get started to unpack this, is with the definition. And so that's kind of powerful, right? When you have this, you have a lot to work with. On the other hand, if you want to prove this, then since it is powerful, you have a lot to prove. You have to prove three things. So when you want to prove this, your proof can actually just become three parts. Part 1 of your proof will be to prove that f is a function. Part 2 to prove this. Part 3 to prove that. And this is an equality, so that might split up into itself two parts. One inclusion and the other inclusion. And this one is just one inclusion. A kind of exception, here I'm saying three things, that's because I'm focusing on the definition. If you have already done your homework problem and finished proving theorem 55, you can use that later, and that might, that tells you, if you already know f is a function, then that, well, I guess that's still three things. To know that this is true, you need to know f is a function, and f is a subset of this, and this is a subset of that. So that's just a different way of framing the three things. Yeah, so where this advice applies is your homework here, for example, when you're proving that this if and only if, for one direction of the if and only if, you'll be assuming this mapping statement, and then you have to prove these other things. For the other direction, you assume the other things, and then you have to prove the mapping statement. So when you're assuming the mapping statement, that's 3 things you get to use. When you're proving the mapping statement, that's 3 parts to your proof, the 3 things you have to prove. Okay, so that's it. Sorry for running so long. I really will try to keep things shorter. I just don't want to skimp on details for this section. I really will try to keep things shorter next time. So yeah, thank you for your attention. I really appreciate it, and I'll see you next time.